Welcome to This Explainer. Look, if you're working in machine learning, you already know the truth. Building the model, that's really just half the battle. The other half, tuning the thing. Think of hyperparameters as the essential knobs and dials you absolutely have to turn before the training even starts. Tuning them well is literally the difference between a mediocre model and a truly great one. So today we're going to master exactly how to turn those knobs. 43 hours. Let that sink in for a second. Say we're working with a standard gradient boosting model, and you've got 6 hyperparameters to tune. If you just test 5 reasonable values for each of those 6 knobs, the math of combinatorial explosion hits you incredibly hard. Even if training takes just 10 seconds per run, testing all those combinations is going to take 43 hours of expensive compute time. That is nearly 2 straight days of wasted GPU time just burning up if you don't know what you're doing.
Now, real quick, before we fix that 43-hour nightmare, let's draw a hard line between two things that get mixed up all the time. Parameters are what your model naturally learns from the data during training. We're talking weights, biases, split thresholds, stuff like that. You do not touch these. Hyperparameters, on the other hand, are set manually by you right before training begins. They control how the learning actually happens. Things like your learning rate or your batch size. You are entirely in control of the hyperparameters.
So here is our game plan for today. We'll start with the hyperparameter problem, then compare grid versus random search, dive into Bayesian optimization, touch on early stopping, look at hyperparameter importance, and finally, wrap it all up with a practical strategy.
All right, Section 1, the hyperparameter problem, otherwise known as how to accidentally burn through your compute budget.
The sheer scale of this problem is just staggering. Relying on naive strategies is exactly how you end up waiting days for results that really should just take minutes. Remember those 6 hyperparameters with 5 values each we talked about? Well, if you evaluate every single possible combination on a rigid grid, a method appropriately known as grid search, it scales exponentially. 5 to the power of 6 is 15,625 combinations. Bam. Grid search might be the most obvious go-to, but as the math shows us right here, it's literally the absolute worst choice at scale. Which brings us to Section 2, grid versus random search. This is where things start getting interesting. This is our first major evolutionary leap in the tuning journey. We've got to ditch the rigid grid. The crucial point here is that random search mathematically outperforms grid search. Researchers Bergstra and Bengio actually proved this. Why? Because most hyperparameters have what's called low effective dimensionality. In plain English, out of those 6 knobs, usually only 1 or 2 actually move the needle for your specific problem. Grid search wastes tons of evaluations, systematically testing completely unimportant dimensions. Random search, by sampling from distributions, covers those important dimensions far more densely for the exact same compute budget. I mean, random search is basically an insider cheat code for machine learning practitioners. If there is an optimal point somewhere in your search space, running just 60 random trials gives you a 95% chance of finding a point within 5% of that optimum. Think about that. You don't need 15,000 runs. You literally just need 60 smart random ones. It's wild. Moving on to Section 3, Bayesian optimization. Time to actually learn from our mistakes. Now, if random search is a massive leap, Bayesian optimization is the absolute holy grail. Unlike random search, which is effectively flying blind and ignoring past results, Bayesian optimization actually remembers its mistakes and learns from them. Let's deconstruct how this works into 2 main building blocks. First, you have the surrogate model. This is a cheap, quick and dirty mathematical approximation of your incredibly expensive model. Second is the acquisition function. This acts as the brain of the operation, deciding where to search next by perfectly balancing exploitation, which is searching near known good points, with exploration, which is searching in totally unexplored, highly uncertain areas. When you're using libraries like Optuna, you'll see a few common acquisition functions popping up, like expected improvement, upper confidence bound, and probability of improvement. Basically, they calculate your next best guess. Because it learns as it goes, Bayesian optimization typically finds way better configurations with 2 to 5 times fewer evaluations than random search. It just doesn't waste time looking in the garbage piles it already knows are bad. Section 4, early stopping and scheduling. Let's save some of that precious compute budget, shall we? I want you to permanently burn this rule into your brain. Not every training run needs to finish. Seriously, if you're testing a configuration and by epoch 10 the validation loss is just terrible, why on earth would you let it limp along to epoch 100? You shouldn't. You need to immediately kill doomed runs to save your compute budget for the promising ones.
So how do we pull the plug? Well, we have a few strategies. Patience-based stopping kills a run if it just hasn't improved after a set number of epochs. Median pruning stops a trial if its intermediate result is worse than the median of completed trials at that exact same step. But Hyperband is the real MVP here. It runs this ruthless tournament-style bracket. It starts tons of configurations with tiny budgets, keeps the top third, increases their budget, and repeats. Hyperband can find great setups 10 to 50 times faster than evaluating everything fully.
And while we're on the topic of training epochs, we absolutely have to talk about the learning rate. It's almost always the single most vital hyperparameter you've got. Keeping it fixed is a huge mistake. Dynamically adjusting it using schedulers like cosine annealing, which is the modern default, or reduce on plateau will give you significantly better convergence than just sticking with a static rate.
All right, section 5, hyperparameter importance. What actually matters most?
Okay, time to reveal exactly which knobs are actually worth your precious time to twist, based on some deep empirical research. This is an essential cheat sheet based on work by Probst and colleagues. Look at the high importance tier: learning rate, number of epochs, and regularization. You should drop 60% of your entire tuning budget right here on those top two parameters. Medium importance gets whatever is left of your budget. And the low importance items like batch size or specific activation functions, honestly, just leave them at their defaults unless you have a very, very specific reason not to.
You also have to match these insights up with the specific model you're running. For a random forest, a simple random search of 50 trials is pretty much perfect. But for gradient boosting or neural networks, you absolutely want Bayesian optimization combined with early stopping. If you're using support vector machines, a log-scale grid search works well since you're really only dealing with two parameters. And thankfully, libraries like Optuna or scikit-learn make hooking up these specific pairings a breeze. Finally, section 6, the practical strategy. Let's put together your concrete workflow. Okay, we've covered the theory, we've got the tools. Let's bring the whole shebang together into a master strategy for your very next project. Step 1, always start with library defaults. They're usually going to get you 80% of the way there anyway. Step 2, run a coarse random search with really wide ranges and early stopping just to weed out the garbage fast. Step 3, analyze what parameters actually correlate with performance. Step 4, narrow your search space and run a fine search using Bayesian optimization. And Step 5, take your winning hyperparameters and retrain your model on all the data. To wrap that up, here are a few rapid-fire practical tips for you to guarantee success. First, always tune your learning rate first. It is the absolute king of hyperparameters. Second, and this is absolutely critical, scale matters. Use log uniform distributions for your learning rate and regularization. Searching linearly between 0.001 and 1.0, that just wastes all your budget on the large end. And finally, use early stopping instead of trying to manually tune the exact number of estimators. Let the early stopping algorithm itself decide when the model is done learning. Now, hold on. Before you go spinning up a massive tuning job, I need to give you a serious warning. Tuning too hard can actually cause you to overfit your validation set. If you run thousands of trials on a single validation split, you are effectively just training your model on the validation data. It'll look like absolute magic on your screen, but it will fail miserably in the real world. You've got to use nested cross-validation or a completely separate holdout test set to get an honest performance estimate. Which leaves us with this final, vital question to ask yourself on every single project. Are you actually tuning the model, or are you just overfitting the validation set? Keep that in mind, use the smart search strategies we talked about today, respect your compute budget, and go make those mediocre models great. Thanks for joining me for this explainer, and I'll catch you next time.